Modern governed systems are highly entangled. Network consensus, cryptographic primitives, and core state transitions are typically blended into a single execution layer. But this entanglement makes formal verification difficult. When the rules of a system are inseparable from the code used to run it, auditing the underlying math requires auditing the entire implementation. To solve this, we must strip away the execution mechanics, the networking and the serialization, to isolate the pure mathematical dynamics of the system. This is the objective of CoV1, a formal category designed to provide the minimal compositional bedrock for any governed system. Forcing this strict separation allows an architect to model and verify the system's core logic independently of the environment where it eventually executes. CoV1 formalizes a system as a single mathematical object defined by this triple: the state space, the violation functional, and the receipt verifier. The specification is intentionally lean. It excludes implementation details like hashing, JSON serialization, and specific networking protocols. Those functions are relegated to external layers, such as co-consensus or co-exec, keeping the core category focused strictly on transition logic. By defining the system through this three-part tuple, we achieve compositional auditability without the overhead of the execution stack. The first component is the state space, X. This set contains every possible configuration the system can inhabit. Next is the violation functional, V. This maps every state in X to a non-negative value representing its level of risk or deviation. The functional allows for a value of positive infinity, which effectively blacklists specific regions of the state space as infeasible. This enables two regimes of admissibility. In the zero-set regime, a state is valid only if its violation is exactly zero. Alternatively, the bounded tube regime allows any state that remains below a designated threshold, theta. Proposed changes to the state are accompanied by a receipt, drawn from the receipt space, R. These are processed by the receipt-verifier, or RV. This is a deterministic predicate that looks at the current state and the receipt to return a simple accept or reject. This framework allows a system to track the analog gradient of risk while enforcing a binary boundary on every state transition. Because CoV1 is a category, we can define mappings between different systems, like System S and System T. We use a comorphism to do this. It consists of a state mapping function that translates positions in S to positions in T. This is paired with a receipt mapping function to translate the transitions. These mappings are governed by the legality preservation law. This law creates a strict logical implication. If a transition is accepted in System S, the mapping must ensure it is also accepted in System T. Crucially, CoV1 does not require the morphism to preserve the violation functional monotonically. Risk values do not have to map one-to-one. Forcing that constraint would exclude many useful ways of embedding smaller systems into larger ones. The category includes an identity morphism for every system, mapping a state space to itself. These morphisms compose. If S maps to T and T maps to U, the legality preservation change through the entire sequence. This mechanism allows architects to scale microgovernance rules into macro histories without losing the thread of legality. When we look at a sequence of these accepted steps, we call it a microtrace. Under the trace closure principle, a history is legal if and only if the verifier accepted every individual step in that sequence. CoV1 does not mandate how these histories are stored or hashed, leaving those requirements to the implementation layer. There is a distinction between syntactic legality, what the verifier accepts, and semantic meaning, what that acceptance implies about the system. To bridge this, every co-object carries a soundness obligation. The architect must declare a soundness contract, a formal proof that an accept result guarantees a designated safe property in the modeled system. Without this proven contract, the verifier's output is just a syntactic signal, disconnected from the physical state of the system it aims to govern. We can see this in practice by looking at the paper A object, which serves as the canonical instance of a CoV1 system. Here, the state space includes a physical budget component, B, alongside the high-dimensional state. In this bounded tube regime, the state is valid only if it remains within the tube, and the budget ticks down as work is performed. The verifier checks the receipt for physical consistency, ensuring tangent cone inclusion and valid step geometry. It validates path integral bounds and checks Shor gap gating for each transition. These checks tie to a soundness contract, guaranteeing strictly bounded budget descent. When the budget is exhausted, the contract forces an absorbing boundary. If the budget hits zero, work stops. The Co-V1 architecture isolates governance into its mathematical components, ensuring the per A